This is the 6th electromagnetism video for A-level physics. The aim of this video is to cover more challenging Faraday's law calculation problem. So it's like the problems seen in the last video, but a bit harder. So example, two square coils, each of width 50 centimeters, are placed into a uniform field of strength 1 Tesla. Coil 1 is initially at right angles to the field, and coil 2 is parallel to it. Each coil has 80 turns. Both coils are rotated through 1 degree about the axis that passes through the midpoints of opposing sides. We will draw this out. If both coils are rotated at the same rate, so they both take the same amount of time to get through 1 degree of rotation, which coil will induce the greatest voltage? Because first of all, we need to draw this out to manage this problem at all. Coil 1. This one's perpendicular to the field, so the field lines pass straight through it. So we could say the field lines come straight out of the page through the loop, like that. You've got coil 2. Coil 2 runs parallel to the field lines, so if the field lines were to come out of the page, again like that, we wouldn't see the face of this loop, we would just see one edge of it, like that. So those are the two coils. Field strength in both cases, B equals 1.0 Teslas. We know that both have, each has 80 turns, so N equals 80. The width, so we'll put a dimension onto coil 1, 50 centimeters, 0.5 meters. The height's the same, these are square coils. Okay, both coils are rotated through 1 degree, about the axis that passes through the midpoints of opposing sides. So that could look something like this. Here are midpoints, a pair of midpoints of opposing sides, and we're saying that it's going to rotate around that axis. On coil 2 it's a bit harder to see, it's going to rotate around an axis that's kind of obscured. It's going to end up turning, if I put this in 3D actually it will help. Right, coil 2 looks like that in 3D with no field lines passing through it. We're going to rotate this one around this axis. Essentially we're going to rotate coil 1 towards coil 2's position and coil 2 towards coil 1's position, but only through 1 degree of rotation. Both of them are going to turn at the same rate, so they'll take the same amount of time to get through 1 degree of rotation. So we'll write that down here as the rate of rotation is the same, the time to rotate through 1 degree is the same. That's good, because if we recall Faraday's law, which as an equation states that the EMF is equal to N multiplied by the rate of change of flux, right, delta phi over T, we'll be able to use the same time for each case. So let's look at case 1, coil 1. Faraday's law instructs us to find delta phi. If we can find that and the time, then we'll be able to compare these. Delta phi is going to be equal to the final flux minus the initial flux. The final flux is a bit harder to find out, we've rotated through 1 degree. The initial flux is not so difficult to find out, right? The field and the loop are perpendicular to each other. So we can say the flux is BA, and we know the area is a square that measures 0.5 by 0.5, that's 0.25. And that applies to both of these. B, we're told, is 1. So we've got some helpful information there. Phi final, so the final flux, we need to use BA cos theta. We established this in a previous video, that if a coil is, or a loop is rotated, the flux through it will be BA cos theta, where theta is the angle of rotation away from the perpendicular situation. The final flux, phi f, is BA cos theta, and we know the angle of rotation is 1 degree, so we can calculate that. BA cos of 1 degree is equal to 0.24996. So we need to write that to quite a few significant figures, because if we round it even to 3 significant figures or 4, it's going to be exactly the same as this, 0.25. Right? And the difference between them is key. We're trying to work out delta phi, which is a very important part of Faraday's law. If we had the two of them be the same, we'd have no change in flux, so that there would be no voltage induced. So we've got to be really quite precise here. You want to go for quite a few significant figures. Okay, so delta phi is the difference between those. So then we need to subtract 0.24996 from 0.25. As we would expect, it's a small value. We get 3.8076 times 10 to the minus 5. To really calculate EMF, we need n times by the change in flux over time. We know n is 80. We've just calculated the change in flux, and the time we don't know. We'll just call that t in both cases. So with this, we're going to end up getting 3.046097 times 10 to the minus 3 over t. Okay, that's as far as we go, because we don't actually know the rate at which this rotates, so we don't know the time it takes. Let's then look at the other case, coil 2. Again, delta phi is calculated as the final flux minus the initial flux. Again, the final flux is harder to work out, just like it was in coil 1, but the initial flux is 0. Remember, if we scroll back to our picture up here, this one, the coil is parallel to the field lines, so there can't be any field lines passing through the coil, so there is no flux. Then to get the final flux, we rely on using BA cos theta. We have to be really careful about theta here. It starts in the position where the field and the loop are parallel, right? That's the initial position for coil 2. So initially, we'll call that theta I. We've got 90 degrees. We rotate through 1 degree. We're trying to get closer to the coil 1 type position. So we're back at 89 degrees. So we can actually work out the final flux now. B, which is 1, A, which is 0.25, the loops are the same, they're identical, and then cos of 89 degrees. And we can calculate that, which is equal to 4.3631 times 10 to the minus 3. Now we can calculate the change in flux. So delta F is 4.3631 times 10 to the minus 3. Right, that's our final flux. And we need to take 0 away from that. So we know delta phi is 4.3631 times 10 to the minus 3. If we apply Faraday's law, n times delta phi over t, we know that there are 80 turns. We've just calculated the change in flux through the loop, And then we're going to divide that by the same time. Again, we don't know the value of time. We're just going to work in terms of t here. So we'll calculate that, and that's equal to 0.349 over t. So now we can compare these two values to each other, right? This is the second case, and then the first case is up here, this one. So let's put those two values next to each other, side by side. Just copy that on down. So that's for coil 1, then coil 2, just bring that down, so then right next to each other. And that's coil 2. Well, we can see, right, and then both of these are EMFs that we calculated, and T is the same on both sides. Well, we can clearly see that this one is bigger. So the answer to the question is coil 2 has the larger EMF or voltage induced. And we've justified that mathematically. Okay, that's that.